Hi, my name is Jordan Skipwith. I'm a senior undergraduate at Texas A&M University, and my study pertained to conducting a geophysical analysis of anomalous extrusive volcanism in South Atlantic oceanic crust. So extrusive volcanism can play an essential role in the accretion and development of oceanic crust, specifically in our case at a slower intermediate spreading ridge in the South Atlantic Ocean. By understanding the processes that control this volcanism, we can begin to understand how the tectonics have evolved over time. So this data set that we studied through our analysis was from the recent crustal reflectivity experiment Southern Transect, otherwise known as CREST. It was a 1,500 kilometer transect that was imaged from the Mid-Atlantic Ridge to the Rio Grande Rise. It spanned 70 million years of crustal ages, and it had slow to intermediate spreading rates from 15 to 30 millimeters per year. So our goal from this study was to analyze the volcanism on the seafloor and correlate this to various factors such as crustal structure, crustal ages, and spreading rates to find some type of relationship. So the main focus of our study was on 5 what we like to refer to as ridge parallel crosslines that were areas measured perpendicular to our transect but parallel to the Mid-Atlantic Ridge. So these all had about 2,500 kilometer squared areas that had varying crustal ages and spreading rates that we could use for comparison. So right up here we have our 5 bathymetric screenshots of each of the cross lines. So what I did is I went through and I identified volcanoes on the seafloor using multi-beam bathymetry and acoustic backscatter. I measured their heights and then used methods employed by Batiza in 1982 to calculate their volumes. And then I used this data to compare it to spreading rates, crustal ages, and abyssal hill formation data from one of my colleagues. So this figure right here shows the comparison between volcanic abundance, or number of volcanoes at each crossline, compared to their half spreading rates and crustal ages. So the general trend is that as you go away into older oceanic crust, you have a decrease in volcanic abundance. However, there is an anomaly at around 31 million years old where we find upwards of 50 volcanoes, which is comparatively large to the rest of the transect. We believe that this volcanic anomaly could be due to increased magmatism from an upwelling mantle, which controls ridge volcanism in the South Atlantic Ocean. So this increased magmatism could cause an increase in volcanic activity, specifically at around 31 million years old. Additionally, the Tristan hotspot, which is located about 800 kilometers southeast of our transect, could be causing an increase in magmatism as well and influencing our volcanic activity at that time. So those are some of the potential causes of that anomaly. So the next thing we did was we compared the average volcanic sizes at each of the cross lines, as well as compared the volcanic distribution at each of the cross lines as well. So generally the average volcanic size stays about the same throughout the transect from 7 million years old to 48 million years old. However, once you get into the oldest cross line at 63 million years old, we see an increase in volcanic size. So we believe that this is due to the influence of sediment cover. So over here at line 1, there's barely any sediment cover, which is shown in this figure right here. However, at line 5, which is our oldest transect near the Rio Grande Rise, you see an evident amount of sediment cover. So we believe that this sediment cover is masking any type of small crustal feature on the seafloor, thus causing us to only find these larger features, causing our average volcano size to be larger at 63 million years old. As for volcanic distribution, it's pretty broadly distributed throughout each cross line. So they have small volcanoes, large volcanoes, and mostly these medium-sized volcanoes in between e to the 17, e to the 19 meters cubed. So there's not really any correlation between crustal ages and this volcanic distribution. And then the last and potentially most important point from our study was that there's an inverse relationship between abyssal hill RMS heights and volcanic abundances. So where you see that volcanic anomaly at around 31 million years old, you have your smallest abyssal hill RMS heights. However, when you get into older crustal ages and see the smallest volcanic abundances, you see the largest abyssal hill RMS heights. So we believe that this supports a paper from Buck et al. In 2005 that essentially said that if you have a larger magma supply, you'll have increased volcanic activity, but if you have a smaller magma supply, you'll have a decreased amount of volcanic activity and more extensional faulting, and thus more abyssal hill formation. So in conclusion, there is a potential inverse trend between abyssal hill RMS heights and volcanic abundance at the same crustal ages in our study. This could be due to the variations of magma supply and potentially a large magnetic presence, especially for a slow to intermediate spreading ridge throughout the history of this ridge segment, specifically at 31 million years old. The increased macrospathic ridge through time could be influenced by a mantle plume such as the Tristan hotspot, which is located nearby. And also, as crustal age increases away from the ridge, volcanic abundance decreases and average volcanic size decreases or increases, likely due to the cause of sediment cover. Thank you for your time. I hope you enjoyed the presentation.